temperature profile in X and Y and Z direction. And then the heat transfer coefficient for the free convection. Just write the top equation. This equation doesn't have the area because area is constant for all of them. It doesn't consider the cylindrical or hemispherical part. It just picks it, and the software is able to calculate that. The introduction of the negative here makes this equation be equal to the upper equation because, see, we have changed the temperatures. The upper equation is T service minus T ambient. This one changes, and for the radiation, it also changes. So that equation is fine to use. And this is the results that I got from both of them. For the theoretical, after slotting in the inner surface temperature, the outer surface temperature, Ts, is given by the data on top. For the finite element, the slotting in this case, the power, because the COMSOL program wants me to put in the power supply and the inner surface temperature, then it calculates the value for the surface temperature as that. And those value looks just froze. They look simple. This diagram here is the diagram of the reboiler after running the program, and then it gives the temperature profile. Like in this case, I ran it with 400 watts supply and 98 degrees centigrade for the inner surface temperature, and it gives me that value. And I had done for the other to get the values for 81 degrees for finite element and 69.
Could you pause just for a minute? The lighter green on the center of the top and the center of the side means it's cooler there?
For the this could be the picture for the this particular picture. If you rotate it, there is some kind of refraction that could be the orientation of the picture. If I rotate this one with the program, it gives a whole brownish color without this refraction kind of. So I would say it's the orientation of the picture.
I think that's just illustrating it's cylindrical is all, isn't it? It's just part of the illustration?
Yes.
Just where the light would show on it?
Well,
Yeah.
Because the bar on the right
The
looks
bar
like
on the
it's
right is
color-coded.
temperature, isn't it?
Because over here it looks like it's different color on this, right? And then on top, is that what, yeah.
Of course, it looks like it's a difference of, I can't read those numbers.
If
Because
it's
this temperature
temperature, if it's surface temperature difference indicated, it is very interesting that it's cooler on the sides, which I would somewhat suspect the natural convection velocity would be more cooling there, I would think. But at the very top, it's interesting. Well, you can go on. That's something to think about later.
Yeah.
Thank you.
All right. So those are the temperatures that I've been for the surface temperature for the finite element using COMSOL and for the theoretical model. And the other experiment that I ran, experiment 2 for the heating, was the cooling model. I now read the reboiler cool down while gathering those data. When the power supply is reduced to 0. The consideration here is that heat transfer from the surface of the reboiler and the content inside is by free convection. So that heat comes out surface of the reboiler and then gets out just by natural convection. My discussion of considering radiation in this case could have been very complicated. Being able to do some integration for the combination of, because if I was considering that radiation was taking place, then I could have added the part of the radiation rows on this side, and it could have given me such pattern. So Dr. Henry said, well, radiation is negligible for the service for this temperature, 98 degrees, and it was now easier for me to equate the heat transfer by free convention to content of heat loss by the reboiler. And the content in this case would be the amount of water inside, or the specific heat capacity of the water, and the mass of the reboiler, Pyrex glass, and its specific heat capacity. Combination of that gives me that, and I've made some assumption to let that value be HA for the heat transfer coefficient, and MCP for the product, for the sum of the product of mass and specific heat capacity for the glass and for the water. Then again, separation of variables and integration put me down all the way to getting an equation that gives a function of HA, which is my value there, and MCP, which is the mass sum, and then the background temperature, TA, which is the ambient, and then the difference in temperatures for the service at time 0 to the ambient temperature. This one is a consideration of exponential distribution. After looking at the nature of the curve for the cooling of the experiment, this one gives an, such an explanation of exponential distribution of heat loss. So after doing this, and I know the service temperature, I know the ambient temperature, I know all those other values, the only thing that need to be known is the HA. And HA is the sum of heat transfer coefficient of the cylindrical part and the area plus that for the hemispherical. The reason for doing this is because they are not equal. The heat transfer coefficient for the cylindrical part and for the hemispherical part is not equal to each other. So we cannot just add them. But we can take the product of the area, the product of the area and the heat transfer coefficient, and then operate with them. Then after that equation and running an experiment, this is the results for the cooling situation for the experiment, the first graph. The second one is for the experiment and the model that I have created from the theoretical values and theoretical considerations and all the dimensionless numbers, but I had to change now the value of the heat transfer coefficient so that it can feed the experiment. Without that, without those factors, the experiment did not feed the model. After doing several simulations with the model, I found a 2.5 factor that should be multiplied by the heat transfer coefficient by the cylindrical part and the hemispherical part to give a curve that best fits the experiment. That's what I got from there. So both of them, this experiment, that is the experiment plus the model with a factor of 2.5 and explained in this slide for the results. The HG value that modeled the experiment was 14.4. And for HH, for the hemispherical part, was 12.9. This was obtained after simulating to make the curve now assume the experiment. And the value that gave me was 2.5. So the deduction I make from this is that our correlation, my correlation of the theoretical model have a difference of 2.5 factor with the experiment values. So using those correlations and then looking at the experiment, then the difference is the heat transfer coefficient is the difference of 2.5 value.